So, as one can see from this slide, put our hands actually on VirtualFluids, the setup and the build and the run of the code will be shown. Before we start, we would like to say that this current workshop is recorded and can be seen later. And here's the QR code for the playlist. And here are other resources. This is the full lecture, the semester lecture for Lattice Boltzmann on the left-hand side. And the rest two are playlists that have small videos that puts the light on different topics in the context of Lattice Boltzmann. So please subscribe, share, and like. Like, share, and subscribe, I would say. So the objectives of this session is as follows. We are going to install VirtualFluids together. This will be helpful also for the next session, for the GPU and CPU session. Also, we will try to run a Docker container. We are going to build the VirtualFluids through Docker. Say something about Git and continuous integration, and these are topics in research software engineering. We'll start with the hands-on setup. Yeah, first we will install the prerequisites, and then we will start with VirtualFluids with Docker and without Docker. We will build and run a simulation and also visualize it. Later I will put the light on the project structure, and then we will see how we work together as a group of developers using Git and continuous integration. So I have asked myself, how would you in 3 sentences define or give an idea about VirtualFluids? Then I stuck with some facts. So VirtualFluids is a CFD code based on Lattice Boltzmann, and it was developed at the Institute for Computational Modeling in Civil Engineering at the Technical University of Braunschweig, and it was under development for 18 years, maybe more. This I have just I just looked at an old presentation from 2022 and added the 3 years. So it was 15 years. So I said, so maybe more. Maybe the guys know more history about the code than me. And this simulation actually was done by Konstantin. I guess this was the this NACA airfoil. I guess what can F-16 wing.
That's not the. There's another F-16.
It's not the F-16 jet.
Yeah.
Old name of airfoil. Developed in the area.
Well, please, whenever you want to use VirtualFluids, do not forget to cite the code. It's now on Zenodo. This is the DOI, and we always have this number, which is the version of the code, because the code is not static, it's growing and being developed. So you can use one version and cite that version, or generally cite the code. Now, about this session, if you want more information, you can visit this page. It contains more details about what I'm currently talking about. And please, I'm the guy who would you like to interrupt. You can gladly interrupt me whenever you feel you have to. It's an interactive session again, it's not like a session. And for the rest of the workshop, for the rest of the upcoming sessions, we need to prepare ourselves. So we have to have these prerequisites. We have to have Visual Studio Code plus an extension called dev containers. We need to install Git, Docker Desktop, and ParaView. this is the minimum prerequisites to install the code on your machines with Docker. If you would like to use the code without Docker, you need to have a CMake, a compiler, MPI, and CUDA. So I would love now to pause and give you some time, whoever wants to download these prerequisites. So once again, I will show this slide. I mean, also my colleagues here would help in that.
So maybe
You said someone who needs file installation. So I guess we asked it yesterday, but nobody answered.
Well, now there is another chance.
You've already installed
something
it.
that we have some issues with installation. So your feedback is always welcome, because sometimes we think everything is fine and it's not, because we cannot test everything with every machine and every version of every OS and whatever. So if you see something strange or that should be different, then please contact us. This would be nice. And then we look into it and we can fix it. Yeah. If not, we always say everything is fine.
So I might ask this easily. Are all these four already on
Yeah,
everyone's
yeah,
machine?
most of the guys that installed it, maybe not with Docker, right? Who have used Docker for installation? Maybe the
Yeah, we need to.
Nobody.
Nobody. Then we have to.
Great. So the guys told me I have to do everything with Docker because everyone would work with it.
Yeah. We have to do everything with Docker.
Examples I use Docker today.
So please.
I would like to learn how to use it because I just can't.
We will come. Okay, so we will hit that part, but then we need now to install Docker desktop and also the rest of the stuff with PowerView.
Yeah, this is something we want to try now to install Docker.
I have it installed. I just didn't get to.
So please.
So we have what version of processor we have ARM.
Okay. Show you how.
Just on my other machines.
Yeah, so maybe Docker is an issue on clusters because not every
Yeah.
cluster provides.
On
On
on you will visit Docker desktop, then get started, then download Docker desktop according to your depending on your machine. So this is how to install Docker. Please visit this website, Docker desktop. So why we use Docker? So before we talk about Docker, why to use containers? Why containerization? So you might have heard earlier this thing. It works on my machine. I have somebody have developed a software, it runs totally okay on his own computer. Then he put it on Git and asked his friend to run it. Then everything goes wrong, and the guy says, "Okay, it runs on my machine." So Docker said, "Okay, we will ship your machine also." Together with the code. This is the whole idea behind containerization. So when code have dependencies, external dependencies, we want to package the code and the dependencies together, and make sure this environment also shipped with the code so that it works on each machine theoretically. So this is the whole idea behind containerization. What's a container? I have mentioned the word container. So this is the definition from Docker. A container is a standard unit of software that packages up code and all its dependencies, so the application runs quickly and reliably from one computing environment into other. So we want not only to ship our code, but all its dependencies. Somebody might ask me, but I have used virtual machines and they work just fine. And here's the difference between containers and virtual machines. In a container, you encapsulate the application code and the dependencies in the form of layers, while in virtual machine you have an abstraction of the hardware itself. So you have a full copy of the operating system. So my machine here, my computer, have one operating system. If I want to use virtual machine, I would build another operating system. So I would have multiple operating systems running on one machine. While when I use container, I use only one operating system kernel and several containers. Not a full operating system, but some lightweight, if one can say, operating system. So you can run hundreds of containers. It would be okay, but only few virtual machines, because virtual machines are heavy, and we're talking about the abstraction of the whole operating system. This is the difference between virtual machines and containers. Now, what is Docker? It's only a realization of it's a container realization. So it's a platform that allows packaging application and its dependencies. And we use it again to avoid dependency conflicts, like different compiler versions, different libraries. And yeah, it simplifies collaboration. So we can easily run the code without the need to install each dependency on that machine. So maybe this graph will make the whole idea about Docker easy. So some basics about Docker. I will start from the middle of the graph, then move to the right, then to the left. So Docker has this thing which is called Docker image. Docker image is a template containing all the instructions, environment settings, and software needed to run a container. So if VirtualFluids needs this and that library, it should be contained in that image. So it's a template, let's say, that contains all the instruction needed to run VirtualFluids. An instant of this image, we call it a container, a Docker container, which we run VirtualFluids inside. Inside this container, we run VirtualFluids. But how to give the instructions, how to tell Docker that VirtualFluids need this and that dependencies? Then we need a Docker file, what is known as a Docker file, which is a recipe that is needed to give the whole dependencies. Any question?
Listen, you have to be a little bit faster.
Okay.
Maybe we don't go through all the details.
Yeah, okay, but somebody wanted to know more about.
Question, please.
If I want to give VirtualFluids to my students pre-compiled, so to speak, can I use Docker?
No, it's like to ship the VirtualFluids with all requirements, with like with a copy of an operating system, a lightweight operating system that would ensure that you won't have problems building the source code, because your computer might have a different compiler, but we ship the compiler with the code and all other dependencies. This is the whole idea.
What do you give the students?
They will have to have specific compiler version that, so for example, I have here Mac, it uses Clang, but we want to unify all this, so we, in our Docker file, we have, for example, GNU. We have an Ubuntu copy of the operating system and a compiler that is GNU. So we sort of unify building the whole code on all machines. This is the idea. Yeah.
I don't know if this answers your question. Like you were asking if there's a pre-compiled version that they only have to hit run as a student.
Yeah, well, if I can use Docker to set it up so I can make it work on all computers.
Right. I don't know, maybe I'm wrong, but if you have both Docker and already ran the make command, that you have everything compiled in the build directory. Maybe this is what he means, that you can do both and then you can pass it on to the students and they only have to run it. No?
Yes,
Because you already
theoretically,
compiled
but we build the code each time from source code inside the container. This is what we do actually.
Okay.
We never have we ever tried to have a pre-compiled version? Okay.
So if you, I guess if you have the same type of computer, then you can distribute this.
Because the idea was, you cloned a fresh version from repository, from Git repository. In another case, you have some old version, or if you have some special version for teaching, for example, you can do it. But for our version, for example, generally we want to have more flexible case, then you have always fresh repository and you can always update the Git repository.
I mean, I think if you say you have a class, and there you have a pool with 20 computers, then you can produce one container and distribute this one container over all these computers. So this is when you have like students in a class, yes.
Okay, so I will continue. We can also build the code without Docker. Lots of you have done this. I won't actually take a lot of time here. So let's try now to build and run a simulation because we're running out of time. So if you did not clone the repository of VirtualFluids, please do. You can, on your terminal shell, try to run this command. Who did not do that yet? So you might want to do this. If you want, there's an alternative option. If you want to be, I use Visual Studio ability. So I will go to my browser and then go to the GitLab code page. Then simply I would say from here code open in your IDE. This is the fastest. Yeah, so I mean the fastest, either you type git clone and then the repository link.
The Docker container should be started.
Yes, but first we so maybe in documents you want to git clone, then simply you get the
somehow we have to start the virtual machine, right?
not yet.
Okay.
It's not yet necessary to start it.
You can check out the
But if you want to run it, it's okay. So after cloning, you will need, of course, to have your Docker running. So I have it already, so I won't clone it one more time. Then you want to open Visual Studio Code and open the folder and choose the directory where VirtualFluids was cloned. Simply these are the steps that are supposed to work. Then whenever we, like for example, whenever we manage to be inside the container, we should simply create a directory that is called build. Then we use this cmake command to build the code, and then compile it. Yeah, and then this is the way how we run our examples in GPU. So we call this line, or in CPU we have to provide extra configuration file. Also, I guess there are configuration files in GPU. Then simply we see the results in ParaView. Maybe I show you this. I will instead of just doing this, I will show you how I do this actually. So I'm currently not in Docker, but whenever Docker works, I simply should open folder and container. I won't do this because I have successful Docker working, so simply I will open the code inside Docker. So this is how it looks like from inside the container. If I want to list what's inside here, I have like these folders. Then again, I have to create a build folder. I think I have one here, so I have to remove it. Yes, I have to remove the current build folder in order to show you how I usually do it. So again, this is how how it should like when you finish opening the code from inside the container. I will create a directory that is called build. Then I will get into build. Okay, sorry. Yeah. Then again, we will keep that and later. So now I'm inside build, then I will call cmake. Then we have different presets. We have CPU version, we have GPU version. So I will call the CPU version because I don't have here GPU preset equals CPU in small letters. Then I would refer to the source folder. The source folder is one level higher. Then I will simply click on enter. Now I wait. I have a successful build, so configuration and generation is done. Now build was empty. Now it's supposed to have some files and folders, and it has the make file. You can see here I have make file, which means that I'm ready to compile the code. This is how I compile it, make. This I provide the number of threads in order to accelerate the whole thing. Now I have successfully compiled the code. I have included only one example, laminar plane flow. It would be found in the bin directory. Now we have a bin directory that contains the binary of this example. So if I went through cd bin, I would find laminar plane flow. I simply want to run laminar plane flow, so laminar plane flow, it's supposed to work, but we have to provide what is known as a configuration file. A configuration file is a file that contains parameters of the simulation that we often want to change. So in order not to recompile each time, we provide them in a separate configuration file. And it looks like this, actually. I have to delete this first. And then in the apps, CPU, laminar plane flow, then this guy here, laminar plane flow.cfg. It contains the path name where the results are supposed to be written. It contains the number of threads, open MP threads, something related to the CPU code, which is known as the block. And here we provide the block lengths, the bounding box, which is the simulation domain dimensions, delta X, refinement level. If we have refinement, I will set this to 0. For example, I do not want refinement on my example, and then thank you. I wanted to say save. Then this is related this is some advanced setup. This is like when you have a simulation that is running on cluster, you don't want to lose the information if one node is damaged, so we try to store the whole status of the simulation at certain time step checkpoints. I provide the out time, which is the time I want to write to the hard disk to write the results. So how often do I want to do this? I say here each 1000 time steps, and the end time is the total time of the simulation. Yeah. So you can provide all these in the configuration file. Now I have to provide the configuration file, but with the correct path. So it's 2 levels above, then apps, then CPU, then the name of the application is laminar plane flow, then laminar plane flow.cfg. Then if I press enter now, it's supposed to start, the simulation is supposed to start running. And it started running. And we started already writing results. So what you will see at the beginning, some meta information about the simulation, and more details about, let's say, the performance, and if the pre-processing was successful, and when pre-processing starts and when it ends, and several information. Maybe on the sessions of the GPU and CPU, this would be clarified in details. I don't want to spend much time. The performance usually is measured with units called NOPS, nodal updates per second. Usually they are in millions, so we have here 3 million or 3 mega NOPS. Yeah, if I was running in parallel, I expect to have like maybe better performance if the problem is large. Now I have written about 90,000. I would stop because I don't want to let the simulation run for that time. Now I want to check the results. So let's see what I did. Now there is a new folder, output, because I'm in the CFG. I have said please write the results to output the laminar plane flow folder. So I want to check the results. I need ParaView for that. ParaView is an open source. Software to visualize, for visualization, I would say. I included it in the information. It needs maybe some time to start. Meanwhile, I want to go to VirtualFluids. Then I want to see where my results are. Build. Then build. Exactly. In the CPU code, you should find at least 4 folders, usually. BC, in the BC folder, you visualize the lattice Boltzmann grid nodes, the status of each node, whether it is solid or fluid, or also the boundary condition type. For each boundary condition, there is like a number stated. If it's, for example, I don't know why it's not working, but let me try one more time. In the blocks, as Martin yesterday mentioned, CPU code is block-based code. So If you want to check how the blocks look like, then you would visit blocks. If your simulation contains geometries or walls, and you want to see these objects, entities, then you would go to geos. MQ is the important one, macroscopic quantities. Inside macroscopic quantities, you would find folders for each time step and a collection of the whole all time steps, the whole fields. So now I click this MQ collection and I want to visualize. Yeah, so this is ParaView. I will click here on apply so that ParaView can now show the simulation. I have here 1, 2, 3, 4, 5 fields. I call them fields, scalar fields. Level is the level of refinement. If you remember, I set level to 0. I don't want refinement, so I expect that level is only one color. Yeah, exactly. It's 0. We have 0 level of refinement. A row, on the other hand, is changing. It's a function of time. So I've called MQ a macroscopic quantities collection file. So all time steps are included in this. If I want to see how the simulation changes as time passes, how the density changes as time passes, I would click here. So we have seen this kind of oscillating at the beginning, then until we reach a steady state case. Yeah, so maybe I will clarify something. This is a channel. There is an inlet, there is an outlet, there is at top a wall, and at the bottom there is a wall. We call this Poiseuille flow. We expect the velocity field in the x direction to have a parabolic profile. So let's check the velocity in the x direction. I would say it's parabolic. I don't know. We can check that, and we compare. And we can compare this to analytical solution as well. I mean, this is how it develops with time, but we can rescale so that we have a unified scale at the beginning. Yeah, we have like 3 components of velocity: rho and level. You can visualize everything here in ParaView. Yeah, this is how you do it. Now this is for building the code and running a simulation. Later, for saving the time, I won't talk about the project structure because Konstantin will go and Martin will go in details, I think, for describing everything. So I will skip this and skip that. I mean, this is also in the source. And if you have noticed, we use Git, and Git is simply a version control software. Maybe I would ask who does not know Git. Maybe this is easier because I guess everyone here is using Git. Okay, then I will skip Git. Of course, you can clone repository. You can push, you can pull, you can do whatever with Git. Yeah, I mean, I will skip also this. And continuous integration, only a couple of words about it. We are working together on a code, so maybe if each one of us is working alone, then some researcher one would develop a feature, then comes researcher 2 and wants to continue developing the code. Then he asks, does feature A still work? Nobody knows. So how to solve such a mess? We work together. So continuous integration is all about working together. It's the practice of automating the integration of code changes from multiple contributors. into a single software project. For that, we use GitLab. And more details about GitLab, pipelines, runners will be on the next session by Martin. I would like to thank you for being here today, and if you have any question, please go ahead.